Every factory, plant, and warehouse exists as a deliberate response to a specific geographic calculation, finding the coordinate that guarantees economic survival. Historically, theorists approached this as a straightforward mathematical problem. The objective was to minimize the physical distance between production and raw materials to keep freight costs as low as possible. In practice, industrial location often ignores pure physical distance. These coordinates are governed by fluctuating spatial margins of profitability and the inherent suboptimality of human decision-makers. To understand the logic of the modern landscape, we have to trace the evolution of location theory, moving from rigid cost minimization models to the behavioral frameworks that account for human error. Mastering this shift from classical geometry to behavioral reality provides the context needed to analyze how physical space dictates industrial success. Weber's 1909 least cost theory used an isotropic plane to balance raw materials and a market. His material index divides raw materials weight by the finished product. When materials lose weight, the index exceeds 1, pulling the factory toward the source to eliminate moving bulk. He mapped the cost of moving away from this optimal point using concentric rings called isodopanes. If cheap labor exists within the critical isodopane boundary, wage savings exceed added transport costs, making it mathematically viable to move the factory. Weber's model relied on rigid assumptions that transport costs increase perfectly linearly with distance, and that managers act as a perfectly rational economic man. Weber provided a mathematical baseline, but his models struggled to account for the physical realities of freight and the friction of human decision-making. Edgar Hoover challenged Weber's linear assumptions. Transport costs are not uniform. They are influenced by fixed loading fees and the efficiency of long-haul freight. Hoover adjusted the geometry of location, showing how straight cost lines transform into curving arcs and steps to reflect the actual pricing structures of the transport industry. In 1939, August Losch introduced a separate priority. Minimizing production costs is irrelevant if a factory is located too far away to capture a market. Losch mapped demand cones rising over the map. These cones represent the reach of a business, showing how market dominance diminishes as the distance from the factory increases. By prioritizing market capture over simple production efficiency, Losch provided a new lens for geographers to define a viable industrial territory. David M. Smith sought to unify these supply and demand perspectives in 1971, creating a model that accounts for both production costs and market revenue. His model plots a U-shaped space cost curve across a 3D terrain representing total costs. An inverted space revenue curve tracks market demand. The vertical distance between them shows profit. Intersections define the spatial margin of profitability, the green zone where revenue covers costs. If a firm operates outside this margin, the cost curve rises above the revenue curve, leading to inevitable economic failure. Smith's work shifted the focus of geography from finding a single geometric point to identifying a viable zone for industrial survival. The models assumed decision-makers act with perfect logic. Alan Pred challenged this with his behavioral location theory, accounting for the limits of the human mind. Pred argued that managers rarely have perfect information, and even when they do, their ability to process and act on that data varies wildly. He mapped this on a 2x2 behavioral matrix of information quantity versus the ability to use it. Real-world firms scatter suboptimally across this matrix, but they survive because they remain within Smith's green spatial margin. Pred labeled these managers satisficers. Instead of searching for the absolute mathematical optimum, they settle for a location that is simply good enough to survive. This proves geographic distribution is shaped just as much by human limitation and satisfaction as it is by the cold logic of cost and revenue. We can apply this entire theoretical progression to modern footloose industries, or swaçon du dieu, which appear to ignore geographic constraints entirely. Traditional heavy industry was defined by the massive weight of raw materials, which dictated a fixed, narrow range of viable locations. Modern footloose industries process highly valuable but extremely lightweight components, like microchips. When the materials have almost no weight, transport costs become a negligible factor. Diamond processing follows the exact same logic. Its incredibly high value-to-weight ratio means global transport costs have virtually no impact on the bottom line. In Weber's terms, these industries have a material index of 1. This causes Smith's space cost curve to flatten out across the geographic landscape. A flat cost curve means the spatial margin of profitability expands to cover nearly the entire map. The economic penalty for choosing one location over another effectively disappears. Without the pressure of transport costs, these firms locate based on behavioral factors, a founder's personal preferences, access to skilled labor pools, or established information networks. By tracking this movement from raw material weight to market demand and human behavior, we can identify the specific constraints that organize the spatial reality of our modern economy.